So we start with the next topic, that is pixelization and quantization. That is a bit something that we already know, but we will see it now with new eyes because we know more. Okay, so pixelization is this effect where you take a number of pixels, a group of pixels, and you compute the average of those, and then you have, if you want, you have regions in the image with different pixel sizes. So the pixel size here is very small, while the pixel size here is rather large. Okay, so this is something very easy. And just a reminder of what we had is, okay, so there is a real world image. This is not the real world image. This is the high resolution image that we store in the computer. But once it is in the computer, once it is discretized, we can still further discretize it more. So we can increase the pixel size within the computer. We can increase the quantization, and we can do both. So the same process that we go from the real world to the discrete image, we can do it again inside the computer. That is what we will do today. Okay, so this is just a representation of those things. Okay, so there are two processes here. So let's say that you want to pixelize. Okay, so you want to do this operation here. Okay, so you have a high resolution image and you want to produce this one. So there will be two steps involved. Actually, we will represent them in multiple steps, more than two. The first one will be, okay, so let's say we have a high resolution image. The first one will be to have something like a low pass filter. So this average, local average, this local average, that is a low pass filter. Then we will do a downsampling. This downsampling, say by a factor, let me check how. Let's say by a factor 10. So we do it by factor delta. Delta takes values like delta takes like 2, 3 integer numbers. And then we do an upsampling by the same factor. And then this is our range. Okay, so this is called downsampling. This is called downsampling. It's also called decimation. And this is called upsampling. And okay. Yeah, those are different operations from the ones that you already know from signals. Okay, so especially this one is not different. But how do you express downsampling? Okay, so how do you say I have a, let's say, let's do it in one dimension. That again it is easier to represent. So you have a signal, whatever that is, and then you want to take one every 2 pixels or one every 2 samples. You want to keep this one, you want to keep this one, you want to keep this one, and so on. Okay, so what is it? Y. This will be Y. This is X of 2n. Okay. This is the downsample. This is the downsample. And typically you can present it also by this operation. Okay. So you do the downsampling by factor 2. Okay. what is the upsampling? And here it is where it is different. Now, let's say that I have this signal, and this is my y of n, that I have downsampled. Okay, so let's say it is this one. And you want to construct a signal that looks like this. So you want to recover somehow the x, but there are samples that you have missed. So you will never be able to recover this one. You will never be able to recover this one. But you want to do the opposite. Okay? So what can we recover? This is the typical upsampling. Let's call it prime, x prime. Okay, so we will keep the same samples where we have them. So I have this sample, so I keep it. Then the middle one I don't have, so I will set it to 0. Then I have this one, then I don't have, and then I have, and then I don't have, so. And on the other side it is the same. This I don't have, this I have, and so on. So these red samples are the ones that are coming from there. Okay, so how do I express that mathematically? Okay, x prime is what? Is y of n half if n is a multiple of 2 and 0 otherwise. And this is called an upsampling. Upsampling. And what else? Yeah, and this is represented by this system. Okay, so let us think now of the pixel size. So all these are samples of the same signal. So there is a signal x of t. Let me try to produce it more or less as in there. And then my original x of n were these samples. Let me do it in green. So this will be x of n in green. So I have these samples of it. This one, I have this one, I have this one, and this one, this one. Okay, so there is a pixel size. There is a sampling rate, whatever. But then I'm skipping one every 2. So I'm keeping this one, and I'm keeping this one. So and this one too. So that means that now for y, the pixel size is twice the pixel size of the original. You see that? So when you do downsampling, if you think of what is happening in the real world, what is happening is that the pixel size now is twice the original pixel size. And when you do an upsampling, you are resampling now at the original pixel size, but now you are missing some samples. What is special there is that instead of putting to 0, you would, for instance, fill with the previous sample. So our way of upsampling, let's say x second, would be this sample I have, so I keep it. The next sample I don't have, but I simply copy the previous one. And then the next sample I have. And the next one I don't have, but I copy. So instead of substituting by 0, you copy. So this x prime x second will be y of n divided by 2 if n is a multiple of 2, and y of n minus 1, 2 if n is not a multiple. So that means, okay, what is different is what happens when I don't have samples. So when when you don't have samples, substituting by zeros makes sense. Copying the previous samples, it also makes sense. Actually, this X second can be decomposed into parts. So I can simulate this thing by an upsampling by a factor 2, the standard one, and then a convolution with this signal. If you compose with that, exactly, this is exactly what it happens. One. Okay, so we will use this kind of upsample, okay? This kind of upsample, the one that we will use up there. Okay, so, and actually this local average is also related to that kind of, so this is disfitted for a factor 2. So I will make it more clear. So it is disfitted. By a factor 2, when you do a downsampling by a factor 2 could be this one, and if you do it by a factor n, it could be 1 over n. Okay, so let's see that. Okay, so let's see it on the slides. So when we go to the downsample image, what we are doing is you take all the original image, you take a region around that point, and then you compute the average. That is exactly this. This is exactly this. So you take the average, and then you take a sample every 2 or n or delta samples in both directions. So let's look at the expression here. Okay, so let's say that there is a very fine sampling rate here. Okay, that we don't see the sample, the small sampling we don't see. We are only seeing the large sampling. And then you are at a given row. Okay, so this row, so you will start at a point that is rho delta, R delta. So this will be the RC pixel in the output. So these are pixels. Let us look at this. Okay, so let's do the downsampling, this operation again. Okay, so this is x of n. I will not draw it now. Okay, so it is somewhere there. And we want to produce y of n. And the relationship is x of n delta. Okay, so what is y of 0? So y of 0 is x of 0. What is y of 1? Y of 1 is x of delta. What is y of 2? Y of 2 is x of 2 delta. Okay, so I'm taking samples, taking this sample here. I'm taking, so now that will be, let's say that delta is equal to 5. So now I'm taking this sample also, this is 5. And then that will be, then I'm taking the next one, that is at 10, and so on. So this is for delta equal to 5. Okay, just to put some numbers. Okay, so in general, and this is what this equation is saying. So this equation is saying, if you have a sample in the downsample image that is at n, in the original image, it is at n delta. Okay, so that is what we are doing here. So in my downsample image, this is the pixel RC. So in my high resolution image, this is at the location R delta C delta. And I have to take my downsampling. I have to take all these samples here. So I have to take this one, but I want to compute the average. So I will take the average of this, and this. And if you look at carefully, this is R delta. This is R plus 1 delta. And this one here is R delta plus R minus 1. Plus delta minus 1. This is confusing. Right. This one here will be R plus 1 delta minus 1. So not R minus 1, but delta minus 1. Okay, so that is what we are doing. Look at this. I'm going from R delta to R plus 1 delta minus 1. So I'm taking all those samples. And the same for C. And then this rho and chi, they are dummy variables just to run over the high resolution image. So at the same time, we are doing these two operations. So we have expressed in a single equation, we have expressed these two systems. So those two systems are expressed by that equation in the slide. Okay, so now at this point, the image is smaller. Okay, it is delta times smaller in each direction. And now I have to do the upsampling. And I will do this kind of upsampling. This kind of upsampling where we are repeating the samples. So here is an example of the process. So you have a high resolution image underneath. This is a big delta, just to highlight the effect. Then you compute the average, and you have a single value for each one of these squares. And now you do the upsampling. So you do the upsampling, and then you copy all this same value, you copy many times in the output image. And now the output image, this is called the pixelated image. The pixelated image, it has this the same size as the original. Okay, so let's put numbers. So let's put sizes. So this is n times n, let's say. Here it is n divided by delta times n divided by delta, and this one is again n times. That's more illustrations of the same idea. Yeah, so this is what I have explained, but now in the slides. And the same for this one. There's nothing. Okay, here you have how to copy. So this is the equivalent of this expression that I have done here. This one there, that is copying. Another way to express it is this one. Okay, so the output image. So the output image at the location rho chi, and this is the band, is the downsample image at the location RC, where rho and chi belongs to a neighborhood of RC. Okay, what is that neighborhood? Okay, so that neighborhood is all the rho and chi coordinates, and it is important to understand where each one of the coordinates live. So these rho and chi coordinates are coming from the output. That is the one that has the same pixel size as the original. So it is a coordinate in the output such that rho and chi fulfill this constraint. So it is r here instead of delta is using s. So it is r delta plus 1 up to r plus 1 delta minus 1. So this is interesting. When you use coordinates, so go up here. When you use coordinates, it's interesting that you define where your coordinate system is. So this is the image here, and a point here will be rho and chi, and we said that the size of this image is n times n. And then the downsample image that lives here, so this downsample image, will have more, it will have the same extent. We are covering the same, where is it? Here. The same region in the continuous web. Okay, so it is the same width, but now the pixel size is bigger. So here, the size is n divided by delta times n divided by delta. So that's annotate the pixel size. So the pixel size here is Ts. Here it is delta Ts. And then R and C are here. So this point, the equivalent point, is R and C. And rho and chi goes from 0 to n minus 1. R and C goes from 0 to n divided by delta minus 1. So where your coordinates are, which is the space of your coordinates, is extremely important. So that is why we have spent some time trying to understand these expressions here. Okay, so here you have examples. So let's say you have an image, and you construct. We will do 8 levels of pixelization. So at the highest level, the block is size 256 to 56, and then it will be twice as smaller in each direction, and 4 times smaller. That from the original image to a little bit bigger pixel size, that there is not such a difference. And now we understand why. Because our visual system acts as a low-pass filter. So we cannot see this small pixel size and the separation between pixels. But then at some point we start noticing. Okay, so from here to there, we already see that the pixels are much bigger. Okay. Then quantization. Okay, so quantization is something we already know. So pixelization refers to the sampling in a space. Quantization is the sampling in colors. So quantization is, okay, there is a continuous variation of the intensity, and then I cannot represent them all. So I discretize this continuum into a set of discrete levels. So all these values here, they will be represented by a single point, and then all these values by a single point, and these values by a single point. And this is the transfer function between the input intensity and the output intensity. And yeah, this is just an illustration of how an image can vary. If we use 16 million colors, or we use 60 million colors. How many bits do you need for that?
60.
How many? What is the most natural number of bits for images? We are familiar. 8 bits per channel, right? So if we have 8 bits per channel, here. So we have the 3 channels, the RGB, and we use 8 bits per channels. So in total you have 24 bits. And then you can represent 2 to the 24. 2 to the 24 is 2 to the 4 times 2 to the 20. This is 16. And this is more or less a million. Okay, it's a number close to a million. It is not exactly a million, close to a million. So this is where the 16 million columns come from. Okay, so this is 16 million colors. This is 16 colors. So 16 colors, how many bits do you need for that? 4 bits. Okay, good. And here again, we have a kind of what happens if I have 8 bits and then I discretize to 7 bits. And again, we have to cover the same areas we have in the space. In the space, we have the same idea. So here, I have a continuous signal, and I have to cover the region where I'm interested in my signal. So if I take a picture of you, it doesn't matter what is the pixel size. This is the field of view that I have, and then I have to cover the whole field of view. What I'm changing is the pixel size. So I have to go from, let's say, those are, I don't know, 10 meters. So I have to go from 0 to 10 meters. And what I'm changing with the pixel size is the steps. But the whole size is the same. So when you make a quantization, you have to somehow follow the same idea. So let's say that the intensity, the original intensity, goes from 0 to 255. So if now you want to do it in 4 steps, let's say, a big delta, I still have to go to 255. Okay, so I will construct something that I don't claim this is the best quantization. There are better quantizations, but this is a very simple one. Okay, so I will divide this in 4 deltas. So delta will be 256 divided by 4. And then my outcome, my transfer function will be something like this. But it still goes, to 255. This is 255. So I have to go from 0, I have to cover the 10 meters, I have to cover the 255 intensities. But now my delta will be bigger. Okay, so we go to 256, but, or 255, but my step will be longer, so that I only need 128 steps to go to 256, or 64 steps, or 32 steps, and so on. And again, it is interesting that, okay, at this point you start seeing artifacts in the background. But up to here, I would say that the quality of this image is almost the same as the quality of that one. So we barely see much of a difference between the two. Probably if you pay attention, you find the small details that are different. Globally, it looks the same. This doesn't look the same. And here you have the same idea now, but now we are covering the same we're plotting the colors that we are able to represent. Okay, so if I go from 0 to 255 in 256 steps, then I use the full 8 bits. Then this is the gray values that I can represent, and then I'm going in steps of 2, and then I'm going in steps of 4, steps of 8, 16, and so on. And why did I say, okay, this is not the best quantization we can do? Okay, so let's say, let's look at this one. Let's say that you have to, you will go only 2 steps, okay, from 0 to 256, which is the best value to represent here. So it is not 0. So this value here has to represent all these gray values. So what is the most sensible gray value to use? The mean of those, and then the mean of these for this one. So actually, a better step function would be this one. So I have to represent the average from 0 to delta, that is delta half. So this would be better. And then the average from delta to 2 delta, so this would be 3 delta half, and so on. So this would be a better step function. Okay. By the way, I was wrong. This is not 255. 255 should be a little bit up. I was right at the beginning. Okay. So if you have to use few colors to represent the region, the best thing you can do is to put the middle value of that region. Okay, so now let us see a few operations that we already know with 8-bit images. So let's say that we have this image, and this image has a feature that there are very dark areas with also very bright areas. So there is a contrast that it makes it difficult to equalize and to see details everywhere. So we can do contrast enhancement. Contrast enhancement, you already know. It is the one that takes the minimum and maximum of this image and maps them to 0 to 55. Okay, it looks more or less the same. What if I do a transformation that enhances the dark values but saturates the high values? You know one of these transformations. Do you remember? The gamma transformation. The gamma transformation with gamma, I don't remember if it is larger or smaller than 1. We don't care. What we want is this transformation. So this transformation is enhancing, so this is the intensity in, this is the intensity out. So this transformation is enhancing the dark values, while this other transformation, this is another gamma. I never remember which one is which, okay? But let's say this is gamma smaller than 1, this is gamma larger than 1. But what is clear, this one is enhancing the bright region. This one is enhancing the dark region. Okay, so these things we already know. Now let's do it with 16 bits. Do you see it? We cannot see almost any difference between working with 8-bit images or 16-bit images. Let us look at the histograms. Okay, so we have the original. And this is with 8 bits. Okay, so the equalization itself, here it is performed with 16 bits, and then you quantize it again with 8 bits. And let's look at this column first. So this column, we already know this thing. So this is the contrast enhancement, this is the gamma transformation that enhances the dark area and the bright area. And we already know this kind of effects where we are creating holes. So there are values in the gray domain that cannot be achieved by this gamma transformation. Okay, so we create these holes, or we create these holes here, or we create this collapse. These collapses here, where we have spikes because two points are going to the same gray value at the output. You remember all these things from the first lecture? Okay, what happens if we do the 16-bit equalization? So you do the operations with 16 bits, and once you finish with 16 bits, you quantize again to 8 bits, and now you don't have the holes anymore. So this image is smoother than this one. This is smoother because there are no holes in the gray values. Okay, so there is no jam, and there is a better use of all the domain that you are given. So you are given 256 values, but here you are not using many of them. But if you do the operation with 16 bits, you are using them. Yeah, so here this is a zoom of an of that region. Here we have the enhanced 8 bit and enhanced 16 bits. And you see that, for instance, this background here, it is noisier than this one. And it is an illustration of this idea that this image with 16 bit is smoother. When you go from one pixel to the next, you can use all the gray values in between, while this one is going in jumps. These jumps created by these holes here in the histogram. Yeah, just to see the difference between the two. Yeah, here it is the same idea. Now, only for that region. So there are many holes if you do the 8-bit enhancement, while in the 16-bit enhancement, there are no such holes. So having a hole in the histogram is bad because you're allowed to use values from 0 to 256, and you are not using them. So you're not using the full spectrum of values that you are given. And then we may next ask, okay, so what is the image? Okay, so let's see. Okay, so let's say I have an image with 8 bits. 8 bits for each one of the channels. And this I can decompose into parts. So this one, I have the first half byte, R1 and R2. Let's call it more appropriate. R high and R low. And then I have green high and green low. And then I have blue high and blue low. So these are high and low. They are 4 bits each one. So that are 4 bits. The 4 highest bits and the 4 lowest bits. Okay, so now let us construct the following image. So from here, I can construct 2 images. So I can construct one. That is this one. We have more space. so I will have this one, and I will have this one. So we have the 3 channels, the 2 half bytes of each one of the channels, and I can have here the high image, and I substitute by 0, and then the green high substitute by 0, the blue high substitute by 0, and I can have the ones with the low parts. This is that. This is green low, 0 blue low. Okay, so we are separating the 4 highest bits from the 4 lowest bits. Okay, so this is the image of the 4 lowest bits. So the 4 lowest bits, except for this region, it doesn't have any information. It's just noise. Then I may try to find an application for this property. So the 4 lowest bits doesn't convey any information, visual information. It is just noise. Okay. So let's say that I have this image that it has 8 bits per channel, and I encode it with 6 bits per channel. Which 6 bits? The highest. No? So I would keep this one, but now instead of being 4, 4, 4, 4, they are 6, 2, 6, 2, 6, 2. Okay. So I keep the 6 highest bits. Okay, so now, so you barely see any difference between the original and the 6 bits per band. But this one, we have removed the 2 lowest bits, so we have this image here. Okay, only that it is 6, not 4. And if we look at the histograms, we have holes. We must have, and these holes must be regularly distributed. Just think of this. Okay, so what is the, if I use 6 bits, what's my delta in gray values? Okay, so what is the, let us look at one of the channels. So let's concentrate on this channel. What is the lowest value I can represent? It will be 0, 0, 0, 0, 0, 0, and then the last 2, they are always 0. What is the next one? And this is number 0. The next one is 0, 0, 0, 0, 1, and then 0, 0. This is number 4. And then the next one will be this one here. This is a 1, 0, 0. And this is number 8. And so on. So what is my delta in gray values? My delta is 4. Okay. Actually, 4 is 2 to the 2, and this 2 is coming from here. So this 2 is this 1. Okay? Okay, then my steps have to be with delta equal 4. So that is what I have. Okay, good. So this is the histogram of this is the histogram of the original image. This is the histogram in which each green value has been represented only with 6 bits. This is the same. Okay, so this is what I was doing on the white screen. Okay, but now I can think of the following. Okay, so now I understand. If I have an image, the most important information is in the high bits. Okay, so that is where most of the information is. So the most important bit, the first one. The second most important bit, the second one, and so on. So I can do the following. What if I have 2 images? Okay, so I have let me represent it only for one of the channels, okay? This will be the red channel. And let's say I separate in 6 and 2. And this is the red channel of image 1. This is the red channel of image 2. And from this image 2, I will do the opposite. Okay? So I will keep only the two highest bits. So this is R1 high. This is R1 low. This is R2 high. This is R2 low. And now I combine these two. I combine these two into a new image that will have. It will have R1 high and R2 high. What will happen? What is your prediction? Okay, so before seeing the result, let us see how to construct that. Okay, so let's say that I want to keep, I want to have those two bits. I want to apply an operation that takes these two bits and put them at the end. Okay, so what is that operation? So I want to construct something that takes this image and produces this one. That is 0 here and R2 high. What do I have to do? Shift right 6 bits. Okay, and then I want there an operation that takes these 6 bits and removes these 2. Okay, so what is that operation? So I want to have something that at the end will produce this one. So we have 0, 0, and here we have R1 high. So that is not a single operation, I need 2 operations for that. But it is very easy. So first, I do midway alpha. I do shift right 2, and then I will have this one. We have 0, 0, and then R1 high. And then I use shift left 2, and then you have that. You agree? A big level operation. Okay, so now I have 2 pieces. I have this piece and I have this piece. How do I add them? How do I combine these two to produce this one? This is the operation I have to do. XOR operation between the 2 words. So I will produce this one. Okay, so that is what is represented in this scheme. So you have image 1, then you right shift by 2, left shift by 2. You have an image 2, you right shift by 6, and you do an XOR between the 2. And then that will be your output image. Actually, you can do an OR. That is simple. And you know digital circuits. So what is simpler, an XOR gate or an OR gate? Which one requires less transistors? The OR requires less. Okay. So So you can say this is an OR, you can say this is also an OR, because you are doing an OR with zeros. So an OR with zeros will give you the right result. So, okay, anyway. Okay, so we have done already that. So this image here, and this is the result I was asking you before. So it has the 6 first bits coming from image 1, the two lower bits coming from image 2. And you don't see image 2. Image 2 is there, but you don't see it. Why? Because we are somehow, our eye is saturated by the first bits that are the most intense. We cannot see this part. Okay, we are driven by the highest bits, and we see this one. So now I want to recover, so I have this word. I have this other image. I have this image. I want to see image 2. What is the operation I have to do? I want to have something like that. I want to have something like R2H0. This, remember the sizes. This is 6, this is 2, this is 2, this is 6. So I want to have that one. And now this is very easy. All you have to do is shift left 6. Then you will have that one. Okay, so we take our image. This is the image that combines the two. You do shift left shift 6, and this is what you have. So that image was hidden. This one. You cannot see it, but it is there. And this thing of embedding an image into another, this is called steganography. Steganography is somehow, stegano is something like hidden. Okay, so you're hiding an image into another one. And you can think of an application of this. So what could this be useful to? For hiding information, for spies. No, but for copyright, this would be a very, very simple way of doing copyright. But if you have an image and you want to keep the copyright of that image, you could hide kind of signature somewhere. You don't need to use the whole image, but you use a region here, and then you put their kind of signature. That signature is not something written like this, but it could be a sequence of ones and zeros that are always the same. So if you find this sequence here of these ones and zeros, that is your image. So they have copied from you. This would be a very silly way of doing copyright. So that is very easy to break. Okay, now let's be more aggressive. So instead of 2 bits, we are over the time. Okay, so now instead of hiding 2 bits, let us hide 4 bits. And now our delta in intensities will be, instead of 2 to the 2, it will be 2 to the 4. So now the delta is 16. And yeah, this is the same scheme, now with 4 bits. And here you have an image, original image. And this is the one with only 4 bits. So this is the original. This is the one with the only highest 4 bits. So yeah, not so different. Now image 2 is in, so the lowest 4 bits they are coming from image 2, but it's still much of a difference. And this is the second one. So this is really surprising. So that image with the trees hidden in this one, and you don't have any clue that there is any tree there. And it is. Okay, so now let us play more with the beats. Okay, so let us say that okay, we were not too successful in this equalization of this image because it had a lot of contrast that were very bad regions with very dark areas, regions with very bright areas, and then none of these transformations that we know, they were particularly successful. But now that we know these things of beats, what we can separate is, okay, let's say that I have this image, I separate in two parts, and one will be the dark region, the other one will be the light region. So now I construct two masks that separate the two areas, and on one of the areas I apply a transformation, on the other area I apply a different transformation. And now I combine the two. Okay, so this is the original, and this is the one in which we have applied different transformations for each one of the areas. And for instance, somewhere where this transformation is very clear is the screen of the computer. So you can see here a lot of details that were much less visible in the original image. So now that we have this idea that, okay, I can separate the dark and light regions based on the bits, I can apply different transformations to each one of those. And here is a surprising result. Okay, so normally we tend to think of noise as something bad. So wherever we have noise, we will have a degraded image. That is not necessarily so. And here you have an application where noise is helpful. So for instance, let's say that you want to quantize your image by a factor of Q. Okay? So this will be our delta. So this will define our delta. And before quantizing, so the typical path would be, okay, you have an image, you quantize it, and then you have your result. And this would give some results like the ones we were seeing at the beginning of the lecture. Here, so you take an image, you quantize, and then you get your output. Okay, but before quantizing, we will add noise. We have to control a bit the variance of that noise, and the variance of the noise. Let's say that image I, the maximum value is M, capital M. So we will define the sigma of this one to be 1 of N divided by Q divided by 4. Okay, so that is, you add a little bit of noise. That is what it is. You add a little bit of noise, and then you quantize. And let us see the result. So, for instance, this is our original image with 8 bits, and then we quantize directly to 4 bits, and we quantize to 4 bits plus noise. And okay, we cannot see much of a difference again, but probably because 4 bits is already good enough to represent an input image. But now you do it with 3 bits. And you see that, for instance, here, in the shoulder, there are kind of artifactual regions. You see that flat areas that are coming from the fact that all these colors are more or less the same, and then you are represented more or less with the same kind of flat area. But if you introduce noise, now every pixel here will be a little bit different from the nearby pixels. And now each one will get a different quantization. So here we are using 3 bits to quantize. Here we are using 3 bits. But in this image, we don't see this artifactual flat area. And that is because of the noise. We can go even further now with 2 bits. And I would say this is a complete disaster of quantization. And here, okay, we are still using the same number of colors as in this image, but it doesn't look so bad. It looks noisy, but it is much more natural than this one. And the same with 1 bit. So you have only 1 bit per channel. Okay, none of the images are gray, but this is clearly artifactual. This is more natural. But it is very surprising, I would say. So this is an application where noise can help before quantization, and this is called dithering. Okay, this technique where you first add noise and then you quantize, it's called dithering. Any question? Around, please. Okay, so then otherwise we move to the next lecture, that is sampling and aliasing. So these are concepts that probably you surely have from 1D signal processing, but now let us do it in 2D. So the problem comes when you have to you increase your pixel size. So now you increase the sampling rate of the images, and somehow you may be creating artificial results. So, for instance, you can look at the grid of this train here, and this grid has kind of artificial pattern in this image than in the original. Okay, so we have done a downsampling by a factor 2 or by a factor 2. And yeah, the pattern is not correct. And that was done by decimating. So we went from this image to this one by taking 1 every 2 pixels. 1 every 2 pixels is exactly the same operation that we defined before. So we define somewhere here this operation here, this downsampling. This is taking 1 every 2 samples. So this is the downsampling that we have. If you do a downsampling, you come into these problems of artificial patterns. Okay, know the reason already. So what happens when you apply this operation? You may have what? Aliasing. So what we are seeing in that pattern at the front of the train is aliasing. So now with images, not with signals. Okay, so let's study this kind of things. Okay, so let's say that we have a signal that is continuous, x of t. This is a reminder of things you already know. And this signal has a Fourier transform that is k omega. And we always draw them like this, right? Minus omega max plus omega max. This is the axis, the frequency axis. And now we take samples. So now you take samples. Let's make them 3. So you take samples every TS. So you construct your new signal, that is x of n. Yeah, let me make, sorry, I want to have more space. Sorry. I want to have more space. Okay, so at the end, we will have this one. And that is something like this. is x t no n ts something like that. Okay, so but there is a step in between. So there is a step in between in which these deltas are not discrete deltas, but they are continuous deltas. So there is a time in which you have t and let us do this one x tilde t, where you have continuous deltas instead of these are Dirac's deltas. All Dirac's. These are called chronic. Then these are chronic deltas. You remember all these differences, right? Okay, so what was the model of x of t? This one here. What was the model? This was x of t multiplied by a train of deltas. So a train of deltas that are separated running out of space. Train of deltas that were separated equals infinity on both sides. This is one. You know that this one is not the height, it is the area of that delta. It's not the height. The height goes to infinity, but the area is 1. Okay, so this intermediate signal, I'm multiplying the input signal x of t times the train of deltas, and I have these Dirac's deltas. Okay, so now, and these deltas are separated, yes. Okay, so now, what is the spectrum of the blue signal? So I will do it here. What is the spectrum of this one? Probably you remember, what is it? This is multiplication, right? So it will be, so x of t omega will be the spectrum is a spectrum. So it will be the spectrum of the first one. Now, what is the relationship between these two? What is the operator I have to put in the middle? If I'm multiplying in real space, I am convolving in Fourier space. What is the Fourier transform of the train of deltas? No. It is another train of deltas. The train of deltas, the Fourier transform is another train of deltas. A constant, the Fourier transform is 1, but not a train of deltas. Okay, so it is a train of deltas, and they are separated. So they're separated by 2 pi divided by ts. That is somehow, this is omega s. Okay? It is the frequency associated to the sampling rate. I will have another here, minus omega s, and so on. And I have to convolve this one with deltas that are located at 0, omega s, minus 2 omega s, and so on. So I have to copy that one here. So this is the convolution with this one. This is the convolution with this one. So this point this point here will be minus omega s plus omega max. And we'll have another one here. And here this point will be omega s minus omega max. And so on. And I have infinite copies of those. So there is a point in this process going from a continuum to a discrete signal in which I have copies. Actually, when you make them discrete, you have the same spectrum, but only that now the frequency axis is rescaling. So now we will have x of t to the j omega. I think you have used this notation for discrete signals, right? Have you used this one? Yeah. Okay, so now you have this one, and now the frequency axis is rescaling. So we have the same. So it goes from omega max to minus omega max. And now this point here, it is 2 pi. It is minus 2 pi. Okay, so now, what happens if, let me do it here. What happens if let me make it green now. My sampling rate is much lower. So my sampling rate is pi t. Now Ts prime is much larger than Ts. We don't need to be much larger. We only need to be larger. Sorry. I'm exaggerating it just to make it more visible. But what will happen? So if Ts prime is larger, how is omega s prime? Is it larger or smaller than omega s? This is smaller than omega s. So this will be smaller than omega s. And I have to copy the spectrum of x, every omega s prime now. So they will become closer. So now the spectrum will be something like this. So I will have minus omega max plus omega max. This is the spectrum of but now omega s prime is smaller. So let's say that it is so small that now the copies overlap. Minus omega s. Now the copies overlap. And yeah, so let's make this is minus pi, this is pi. When I do the rescaling of the frequency axis, when I do the rescaling, so now omega, let us keep so this width should be the same as this one, okay? This is minus pi to pi. Minus pi to pi stay fixed. But what I see is that now my spectrum seems to be wider. So my spectrum seems to be like this. And this copy that is here at 2 pi, it is also wider. And I'm not drawing the one at minus pi, so let's put labels again. So this is x, a, b, omega, and that is omega. And now I have an overlapping region. So in this area, I have the spectrum, the right spectrum that I wanted, but I have a contribution from the nearby copy, and the same happens here. So here you have also a region that is invading your area. And this is the aliasing. So aliasing is an effect that always occurs at high frequency. And the problem is caused by a too large sampling rate. So if you have samples that are very far from each other, then the spectra overlap, and then we have a mixture of the spectra at high frequency. What else? What is the solution? What is the solution? If you want to sample, yeah, there are two important comments here. One, what is the condition? We will go now to the solution. So, what is the condition so that aliasing doesn't occur? Okay, so let's look at this point. So, what do we want? We want, let us look at this. Let us look at this. We want that omega s minus omega max is larger than omega max. What is the same? Omega x is larger than twice omega max. And you may recognize this. What is that? It has a name.
Nyquist.
Nyquist. Yeah. So this is Nyquist condition. So you have to sample at a frequency such that this is respected. And okay, what is the solution? So to make sure that this is fulfilled. So if you know that your sampling rate will be omega s prime, what you can do is before downsampling. So this is a sampling. Okay, so before multiplying, so I have my seed x of t. At some point, I will multiply by my train of deltas that has sampling rate ts. Now we forget whether it is ts or ts prime. We don't care. And this one, I don't know what is the spectrum. Okay, but I can do something before. I can make sure that it is limited to omega s minus omega s half. Omega s half. I can put a low pass filter. And this is a low pass filter. This is omega. This is and that filter has a name. It is not difficult to know. What is it preventing? It's preventing aliasing. So this is called the anti-aliasing filter. Anti-aliasing filter. Okay, so before sampling, make sure that you will not have. Make sure that this spectrum, the maximum frequency is omega s half. So, for instance, let's say that with Ts prime, we don't fulfill this Nyquist condition. So the anti-aliasing filter, after the anti-aliasing filter, at this point, the spectrum would be something like this. This guy, okay, at omega s minus omega s. And this would be the spectrum of the low pass filter version. And now you can sample. You can sample, and then at the end, at the very end, your spectrum would be something like this. So length of A J omega would be something. This is minus pi pi. And then it is repeated. But you don't have aliasing because of this filter. Yeah, that is another representation I like. Let's see if I can find it easily. I'm sure I will. So let me go to this, and then teaching, and then this one. So there is another implication of this Nyquist condition. So another way to read it, the Nyquist condition is the following. So we go like this one here. Okay, yeah, like this. Okay, so another way to see it is, if you want, so Nyquist guarantees that there is no aliasing. Another way of saying that is, Nyquist guarantees that you will be able to recover the continuous signal. So we started with something continuous. Let's see here. We started with something continuous. We went to the discrete world, and then Nyquist guarantees that from this sample you can recover the continuous. And here you have an example of that. Okay, so let's say that you have a continuous that is the pink signal, and you take all these samples. If these samples fulfill Nyquist condition from the blue samples, you can recover exactly the pink signal. This is a little bit surprising. It wouldn't seem to be the case, but if and this condition of twice the maximum frequency can be thought of so in this way. So let's say that you have a wavelength. Okay, so I have this distance. If you have at least 2 samples per wavelength, you will be able to recover your signal. So let us count. Okay, so I have 1. Let's go from maxima to maxima. So I have 1 and 2 samples here from maxima to maxima. I have 1 and 2 samples. So I have 2 samples for every wavelength. So if you have 2 samples per wavelength, you can recover your signal. If you have many samples per wavelength, so let's say that you have a continuous signal that is like this, and you have many samples. It is obvious that you will be able to recover your signal. Okay? You have so many samples, you see your sign there. And let us keep less and less samples, that is increasing the TS. So now let us have the same signal. So I have the same signal here. All the two labels. This is T, this is T, and we have the same signal, same. But now I have many less samples. I have 1, 2, 3, 4. Okay, it doesn't look like a sine, but I can recover the sinusoid exactly, and that is given by an Nyquist. So if you have in a wavelength, you have at least 2 samples. 2 samples is not the limit. You may not be able to recover, but if at least you have a little bit more than 2 samples, then you can recover exactly your signal. That is what Nyquist is saying. And here is an illustration of breaking Nyquist. So let's have less than 1 sample less than 2 samples per cycle. So Here I can recover. Here, let us count. I have one sample here, another one there. So maybe this is on the limit. Let us look at this cycle. I have only one sample. So there are cycles for which I have two samples and cycles for which I have one sample. So I cannot recover this one, I cannot recover this one, and I cannot recover this one. Even this one. It seems, if I only know the blue samples, it seems that my sign is much smoother. That is aliasing. You see? Aliasing is, let's go to here. Where do we have aliasing? Here. This is our aliasing. Okay, so let's say that our spectrum is only made of a couple of deltas. Okay, so this is X. I will not do anymore the argument because it is clear. So this is our spectrum. We have a tone, single sign at that frequency. Let me have more space. Okay? So let me have more space. I will draw them more separately. So the idea is the same, but they will be more separate. Okay. Now, by this is omega naught. This is minus omega. Okay, now I have aliasing. Okay, I have fewer samples than required. Okay, what is the spectrum of X tilde? Okay, it will have this copy. Will have this copy, and I will make the other copies in different color because otherwise it would be difficult to distinguish. And let's say that omega x is very similar to omega 0. It's a little bit larger, but very similar. So I have to make another copy from here, but this copy from here will be this one, and this copy, I will have another one over there. And then I will have another copy, this is copy at omega x, and I will have another copy at minus omega x. But the copy at minus omega s, that will make it blue, will come to here. And now, omega s have, what color to use? This one. Omega s have and minus omega s hat will become pi and minus pi. Okay, so now my spectrum will look like this. So I will have copy, another copy, and then I have a minus pi, pi. And this is X, AJ. You see, so two signs, or one sign that is relatively high frequency, it appears as if the sign is very low frequency. This is what's happening here. So from the blue points, it seems like as a low frequency sign. So that is this thing. That is this thing here. But actually, I'm not seeing the right copy. The correct copy is outside my spectrum. It is somewhere here. So what I look at, that is this region of the spectrum. Actually, they are the LEA's copies of the nearby spectrum. None of them are coming from the red. Um, okay, so these are illustrations of this idea, but now with images. So let's say that we have an original image, and then we have a power spectrum. And this is the decimated image, and it will have a power spectrum that is aliased. And we will see how. There is I think it is nice to see now. There is a video that nicely illustrates this idea. Okay, so this will be. This is a movie. They recorded this wagon movie, and if you look at the wheel, it seems. Look at the wheel and the radii of the wheel. They seem to be fixed. So fixed means zero frequency. So that is we are taking. So it is turning. I'm taking a sample every, I don't know how many milliseconds. So I'm taking a sample at this point, and then it turns, and I'm taking another sample, that is another picture. But it looks as if in these milliseconds, there is a whole turn. It seems as if, we don't know how many turns we have, okay? But it looks as if it is a whole turn, and I'm taking the same sample there. So that is, it is exactly this. Now the two suns have collapsed to zero frequency. So let us look at the video again. Let me see. So it is turning, and then the camera is taking a picture every 24 frames per second. Have you heard of this? A monitor has 200 frames per second, or whatever number of frames per second. So this is the same. And here it is even more notorious. So here the wheels are going backwards. That is. Some of the wheels they seem to be moving backwards. You see? They look slower. Look at this one. This is going backward. It is desaliasing. So you can have aliasing with images too. So you can have it in space, as we had in here. Aliasing in space. Or you may have it in time with the video. Okay, so